The real advantage of EFI is not just in its ability to accurately supply the engine with fuel and spark, but to also ensure that those requirements continue to be met as atmospheric conditions change. In order to achieve this aim, the ECU will contain several compensation tables that are used to adjust the main fuel and ignition numbers as operating conditions vary. Most ECUs will at least contain an intake air temperature compensation table and a coolant temperature or warm-up enrichment table, but beyond that, the sky's really the limit. Maybe we want to add some extra fuel or remove some ignition timing above a certain road speed to protect the engine. Or maybe you want to reduce boost pressure when the engine gets hot. Depending on the ECU, you can achieve almost anything that you feel is necessary. Let's discuss the intake air temperature compensation in a little more detail, as this is a compensation I know a lot of tuners struggle to understand and correctly tune. By this point, you should understand that air density is affected by air temperature, but if you need a refresher, you can check back to the module on air density from earlier in the course. From that module, we learned that the formula for air density is equal to the air pressure divided by the specific gas constant multiplied by temperature. The calculation we looked at earlier used imperial units, as we wanted to calculate mass airflow in pounds per minute. However, it's still more common for ECUs to work in units of degrees C, so in this module, we're going to use metric units. Most air temp compensation tables consist of a two-dimensional table relative to air temperature, and the temperature breakpoints will usually be every 10 degrees. If we calculate the air density at each breakpoint across the air temperature we might expect to see across the normal operating range of the engine, we get the graph shown. For this graph, I've kept the air pressure at 101.3 kPa, so the only change is to the air temperature. Remember that changes in air pressure are dealt with already by the ECU's fuel model, so here we're only interested in temperature. The result of the calculation gives us the air density at each temperature breakpoint, but that's not particularly useful to us. What we really want to know is how the density changes between each breakpoint, or more specifically, the percentage difference. If we know what the percentage difference in air density is between two zones in the table, we then need to make the same change to the fuel delivery in order to keep the air-fuel ratio constant as air temperature changes. As you can see from the graph, the relationship between air density and temperature isn't perfectly constant, and if we want to be completely accurate about tuning the compensation table, we can simply calculate the percentage difference at each site and enter this into the table. Remember that as air temperature increases, we need to reduce the amount of fuel because as air density decreases, we have less oxygen. While the relationship between air temperature and density isn't linear, it's still quite a close approximation over the normal range of temperatures we're likely to experience, as you can see by this trend line fitted to our graph. An easier way of filling out the air temperature compensation table then is to use this approximation, which gives us a change in air density of approximately 3% per 10 degrees C. Based on this, we want to add 3% fuel for every 10 degree drop in air temperature and remove 3% fuel for every 10 degree increase. We still need an arbitrary 0 point in this table where no compensation is being applied. Since standard temperature is considered to be 15 degrees C, it makes sense to use this as the 0 point. Of course, it doesn't really matter what we choose as the 0 point as long as we're making a 3% change every 10 degrees, and often these tables will have fixed points and you may not have a site at 15 degrees. In this case, I'd normally set 20 degrees as the 0 compensation point and we can work from there. How the intake air temperature compensation is dealt with in the ECU also varies depending on how the fuel model in the ECU is handled. If we take, for example, an ECU that uses a mass airflow sensor for the load input, the MAF sensor directly measures the mass airflow, and hence the effect of changing air temperature is compensated for by the mass airflow sensor. In this sort of ECU, we may not have any additional compensation tables based on intake air temperature. If we're tuning an ECU that works on the speed density principle on the other hand, then there are two ways that the air temperature can be dealt with. Remember that the speed density principle calculates mass airflow rather than directly measuring it, and it does this using the ideal gas law, which we're going to learn about in a little more detail further into the course. For now, all you need to know is that the air temperature is a variable in the ideal gas law. Some ECUs will provide a separate intake air temperature fuel compensation table that's up to the tuner to configure, while others, and particularly those ECUs that use a VE or volumetric efficiency based fuel model, will often account for the intake air temperature directly within the fuel model. It's important to understand how your particular ECU works so you know how to deal with the air temperature compensation tables. Summarising this module, compensation tables allow the ECU to modify the fuel or spark delivery in order to meet the demands of changing atmospheric conditions. Most ECUs will include a handful of basic tables to compensate for things like air temperature and coolant temperature, as well as the warm-up process, but an aftermarket ECU also allows us to add further custom tables to provide all kinds of solutions. While air temperature is one of the most common compensation tables used, it's also the most misunderstood. Take the time to properly understand how it works, and you'll quickly start seeing huge improvements in the consistency of your tuning work.